Good, here we go. Hello, guys. How are you? All good? Are you ready to die? No, I was meaning to ask if you are ready to continue, or is there anything you want to solidify? I mean, I am going to have to trust you. I'm constantly receiving feedback saying, it's a bit too much, it's a bit too much. I like that. But I don't want to rush ahead now that we've discussed some more complex things. Is there anything you would like me to repeat, discuss, demonstrate, something that's not really clear? No, great. We can go on? Let's go on. Okay, so I'm thinking, shall I make a choice? I mean, it's difficult to make a, let's see if we have a majority vote for either of these. Because one thing I could show you, which is really exciting, is a feedback FM. Okay, because the feedback itself is the most miraculous things in mathematics, if you ask me. I had to, I think last year as well, you know, even though it's not anything like entry-level stuff, I always have to discuss a bit of chaos and all the rest. In fact, it's really interesting to discuss what happens to a sine wave if you feedback to the phase. You can actually feedback a sine oscillator into itself as well. But the really interesting thing is that you can feedback everything. You potentially know about the no input mixer genre, yeah? So you have guys who would stand out with maybe even this size mixer. I mean, as long as you have an EQ, it's good to have a lot of buses, because what you do with a mixer is you just feed everything back into the lines, all the outputs back into the line ins, and it's going to start to make really weird things. If you have a feel for it, and if you can find the weirdness. And it's probably the most exciting thing. So I can show you the FM feedback. Well, we could look potentially at this sine wave feedback. I remember in SuperCollider it's kind of tricky because it's part of the FM story as well. The actual real hardcore signal processing engineers don't call it frequency modulation, what we do. They call it phase modulation. And the reason is that once you start modulating an oscillator with those depths at those rates, you never get a frequency. You know, so you know, to get a frequency you need a whole lot of sine wave, you know, or something similar, a whole lot of so actually technically the inputs to the sine wave whereby you control the frequency would be the phase input, really. And when the programmers don't have this perspective. With programmers, what you have in SuperCollider is that you have an actual phase parameter, which is just the delay, the offset kind of thing. But it's very interesting because let's just run this as a mental experiment, which is probably the most challenging thing I imagine these days. So if you imagine that a 0 at the phase input doesn't do anything to the sine wave. Now, if you have a positive value, it will, so to speak, speed up the sine wave. In other terms, it will heighten the frequency, right? If you give it a number lesser than 0, then it will slow it down, the phase, and it will lower the frequency. So what happens if I take the sine output and feed it back to itself, right? Because I have a -1 to +1 range coming out of the sine oscillator, as usual, which means, right, that what will happen is that as the sine wave starts playing, right, my phase modulation is going to spit out positive values. So it will actually compress the sine wave, it will speed it up, right? But actually, because the period of the modulator is the same as the oscillation period, what you will get is that it will squeeze in the first half. So of the sine wave, the first half will become shorter, but then it's going to go into the negative values and it's going to squeeze out the rest of it. And actually it will come back into sync with itself, right? So actually it's going to modulate only the waveform, right? Because by the time I'm out of the single period, right, I've already been up and down in phase modulation. So actually I have squeezed the first part, stretched the second part, and I'm bang on time for the next period. So actually if you feed back a sine oscillator into itself, you kind of get a timbre change, right? Because the basic pitch won't change. The sine wave is symmetrical around the zero line. So as much as it speeds up in the first half, that much it will slow down later. Okay, so that's an interesting thing. And actually what you see from the sine wave, it starts to kind of squeeze in. But I remember there were some issues with implementation, so I probably don't want to go there. But the other interesting thing that I might show you would be is what happens if I take a sine wave in its period and just shorten it. Run it up and down very quickly, and then leave silence. Okay? So the period duration stays the same, but I'm actually pulling the sine wave in and out. And that's a really useful thing to see. I mean, hearing it, it will change the timbre. Great, it's a buzz. Whatever you do to it, it's a buzz. But the really interesting thing to observe at that stage is that, you know, it's not the curvature of the sine wave that makes the frequency, that makes a pitch. Because this is kind of the intuitive thing that we get. So it's a kind of a nice little myth buster as well. So what do you guys prefer, feedback or a bit more essentially wave table oscillation type stuff? Feedback. Okay, cool. Great. Well, it doesn't mean I won't leave it out. You understand it's our last class in live until December. But we've done, I mean, except tomorrow, obviously. Or is it day after tomorrow? Day after tomorrow? Tomorrow, yeah. So as far as that goes, I mean, we've done well. We're supposed to do 12, 14 hours in a semester, and we are already past that mark. And that's because you guys told Balázs that you're really interested in this stuff. So I was like, okay, let's do a Wednesday edition as well. So that's what we're doing. So I think in that period, you know, I will ask you to just play with the stuff that you've learned, because, you know, that I think that's the main thing, that it becomes your language and that you make some music, whatever you think is music. Hopefully something we don't think is music. Okay, so let's look at the feedback stuff then. It's quite exciting, and the first basic thing we can do is actually FM feedback. So here is my basic little FM patch. So what I'll do then is I'm going to take this oscillator. I'm probably well off doing another range conversion as well, because this allows me to do two things. So you see, this kind of range conversion, multiplying, adding, is all over the place. You've seen that every UGen has these controls as well. And you've seen what are the terms that we use in an FM patch. But actually, typically I refer to this as a multiplier, because you multiply with it, and this as the adder, as you add with it. And then in this context, those are valid names, but in every other context it might be slightly different. In fact, this set of names come back only in FM, really. Okay, so I'm going to try to produce this patch. Right, so I mean, it's a bit, I'll probably have to do this, yeah, just so you don't get confused, that this is the output signal from the sine oscillator, and then it goes back to the original modulator. So you can think already, right? So it's really important that you kind of can start imagining what might happen. I mean, I think, you know, before you can get really creative with the code, it's much easier to get really creative with drawing, right? So what do you imagine happens here? Well, this is a sine oscillator that we're going to hear, so it's gonna stay -1 to +1 range, okay? So if I have I have a 1 here and a 0 here, so to speak, default values, then actually this modulator will go up and down in frequency, right? So actually what I can do here, if I want to keep this 5 as the center frequency, in this case it's a modulation frequency, what I can do is I can make that the adder, right? If I say this is now 5, right? I've kind of taken out the parameter from the sine oscillator, the fixed value, and I've made it the fixed offset, you see? So typically from here, I will have a bipolar signal. It will be centered around 0, right? So actually this becomes my modulation default frequency, so to speak, right? And then the value that I put in here, how would you call this one? This value would actually be, you see here it's a depth. So I could call it feedback depth, but actually I can call it amount of feedback as well. So it's essentially going to tell me how radically I'm going to change the values around this center value. Okay, so if you imagine this as a basic setup, you might say, let me just grab the charger. You might say, well, actually it's a bit funny because you see we're kind of developing higher frequencies as we go down the patch. You see, in your initial experiments, you've probably seen that, you know, modulator has a lower frequency than the carrier, typically. But actually, if you have thoroughly understood the harmonicity and the index of modulation parameters of the FM, then you should have, you know, be stunned a bit by the fact that if I have a modulation index that is larger than 1, then my modulation frequencies are higher than my carrier frequency. You see? So that's the one. Maybe that's the first thing to start with. Let's try this. Let's see what happens. Okay, so I have a sine oscillator here. And then I will call it A. And I will take, well, fine, 92 Hertz. And then I will have my final sine oscillator, my carrier, and the frequency will be A. And actually, I can put the range here as well. It doesn't really matter, 400 to 4000. Let's have a radical range, okay? I misspelled post, did I? Probably didn't select things quite well here. Oops. Okay, that's your typical FM sound. Now the interesting thing is what happens, well actually you've seen me do this with ramps, right? So I'm going to do a ramp here. I'm going to start at 92. In fact, whenever I'm in frequency domain, exponential ramps are more useful. I'm going to start with 92 and I'm going to go all the way up to 10,000. I want to go above the carrier frequency. See what happens. Because it's a kind of a, wait a minute. So how can I change the frequency faster than the actual oscillator that's making it, right? It's a kind of a, it's a wrong thing. And that's actually part of the reason why the accurate term is phase modulation, as I explained. So let's see this happen. Is this ready to go? Oh, that was very short. So let's go through 30 seconds. Cool. So you see that actually it is throughout an FM sound. It doesn't suddenly stop when the modulator is faster than the carrier, right? So it comes through. Now, anyone want to tell me what were these? Why did I hear these things happen? What contributes to those things? So the point is that, you see, if you remember, the modulation frequency actually directly determines the distance of the sidebands, right? So if it's a 5 hertz modulation, I'm just going to get them 10 hertz apart. But if it's 50, I'm going to get 100. If it's 5,000, I went up to 10,000 modulation frequency, right? And you understand that actually both 0 hertz and the Nyquist frequency are mirrors. So everything that starts to escape starts to come back. And with 10,000 hertz frequency modulation frequency, right, I'm throwing every sideband 10,000 hertz away and away. So it's like huge spread, but it's within a very narrow window, so to speak, of mirrors, right? So that's why you get that actually a sideband is escaping, mirroring from the Nyquist, going to 0, mirroring from the 0, mirroring from the Nyquist, mirroring from the 0. Right, to actually get all these mirror images going up and down really intensely. That's what we hear. But the actual character, the fact that we have these sidebands which are essentially inharmonic, right? They don't have integer multiple relationship to the fundamental. They're always offset by a fixed value. Because they are still there, no matter how many times they've been reflected, actually we still get just an FM type sound. Okay, so actually there is nothing to worry about in terms of doing that. Okay, so now we're coming to the point then. Let's try to produce a feedback thing. So in SuperCollider, I mean, worth saying, because it's it's kind of part of the theory, but it's definitely worth mentioning that feedback in digital domain is impossible. Pure feedback. You have to have at least one sample delay. You just cannot do without it. And once you're in the analog domain, if you do this with analog synthesizers, feedback stuff, it is instantaneous, right? In fact, it's really interesting to consider how the hell it happens, and there's some conspiracy theories around this as well, that, you know, the current in a circuit will not run until you connect the feedback, right? So that's also very deeply dependent on the feedback. If you disconnect, it just won't run. You cannot make the current run from one point to the other. It has to be grounded. There has to be a loop going, which is really funny to consider as well, right? So in the analog domain, it is actually, well, actually, I probably shouldn't use that word, but it seems instantaneous. In the digital domain, you have to be at least one sample delayed in order to calculate the next sample, right? And, well, one sample, what is it? It's how many milliseconds? 1 millisecond. It's actually less than the 10th of a millisecond. About a 20th of a millisecond if it was 50 kilohertz. So actually, if you do this in the analog domain, that's a significant value. You know, it might seem like, well, it's just one sample, but it actually does things. So the kind of stuff that you can do with feedback in analog synthesis is the kind of stuff you have no chance, theoretically no chance to do digitally. And actually, when you come close to doing similar things, it sounds different. It definitely sounds different. It's the analog feedback is much more real. It actually has some really interesting properties. It's probably my favorite thing around anyway. So having said that, actually you don't even get one sample feedback because you have the computer, I don't know if it has occurred in other classes, but there are buffers running, right? So actually the thing to understand is that it takes a lot of cycles, CPU cycles, to set up a calculation. In relation to how long it takes to run the calculation. So actually that's why it's much more efficient to set up a calculation and then run a buffer's worth of samples through it, and then set up another calculation and run the whole buffer of samples through it. You probably know that once you increase the buffer size in any software, it's going to decrease the CPU load. If you decrease the sample size, it's going to increase the CPU load. And that's why. So actually, you could do down to 2 samples, I believe, in SuperCollider if you would set that up to have the software buffer size that low. By the way, Bella, which is an embedded hardware programming thing, I don't know if you've heard from Queen Mary University, does run SuperCollider and does do hardware 2 sample delay, which is, well, probably not unique anymore, but definitely 10 years ago when it all started, it was wow. You know, it's much lower latencies than any laptop or a sound card could give you. Okay, so let's see this feedback running. It's gonna run at least, as I said, with the block size delay. And the way we work it out is we have 2 UGents. We have the local in.ar and we have the local out.ar. Okay, these are the 2. And essentially, what you send out with the local out comes back into the local in. Okay, I guess you guys are used to checking out the help files as a first thing around. And here is a decent example already. So you see the way it's used is that essentially the final signal that I'm listening to in this case is sent to the local out, and then it is just sent out to be heard. Now here you have already, you are reversing the 2 elements in the list. So I hope that's clear that if you that to get a stereo signal, you actually have a list of 2 signals. And this will reverse them. So the left goes right, the right goes left, and you have times 0.8, which makes it such that it decays over time. It gets more silent. Okay, so that's the local out, and then whatever you have sent out there, you can expect to have it back here. Okay, now what you have then is number 2 in local in, which is the number of channels. Okay, so in this previous example that was local in 2 because you had a stereo signal feeding back, but now I'm going to have just 1 channel. Okay, so essentially if this is my B signal, then I'm sending out the B signal and I'm making it audible. Huh? Funny how the tab stops working at some point. And then here I can actually use that signal that has been sent out here. You've probably seen it, might have seen it in Max MSP, tap in, tap out. It's a very similar thing. Okay, so the question then is, how do I utilize this feedback signal? Well, first of all, it has to go in here. Well, what I can do, I'll just call it an F for feedback. Okay, so what I'm going to do then is I'm going to say that the frequency of my modulator will be F times, well, I'll call it feedback depth, and plus feedback, or I should call it just modulator frequency. Okay, so this is akin to what I have just drawn. So this allows me to specify the feedback depth, and if I specify it to be 1, then nothing happens. And I can specify my modulation frequency to be 5. So if our hearing, What am I doing here? Oh, I cannot use capitals, sorry. MF, F, D, MF, how about this? Another semicolon. Local out B, another semicolon. Funny day today. Okay, so now I hear the regular FM. Is it a question? Just the inspiration, I hope. So I actually hear 5 Hertz modulation between 400 and 4000 Hertz. Okay, so now I can start to have some fun, I hope. And I'm gonna check out what's gonna happen. And let's do this exponentially as well. If I increase, well, it will go audio rate, the feedback depth starting from 1 going to 5000. I'm gonna keep my finger on the mixer. And I want to hear this over 30 seconds. Is it... Okay. Okay. There we go. That's probably the end of it. Okay. So that's that. That's your chaos. So you had oscillation, you had probably there was multiple point oscillations, and you had a kind of chaotic noisy thing in the end. And the fact that it's nothing like a linear thing. It's not like you know, if I had this on a dial, it would be like, wait a minute, something's broken, right? Because it doesn't do anything for the first 30-40%. Then it starts doing something, and then it goes into noise. And also what is very characteristic of all the chaotic stuff is that you get ranges where a lot of things happen, and you get ranges where nothing happens. Okay? So actually let's try to find that range, which is really interesting. So I'm gonna pull these values so I can read them. So this is my feedback depth. So you see actually, oh, there it went freaky. Okay, and now, 250. I want to play around 250. So let's see what happens between 240 and 290. Okay. Did it sound anything like what we heard just now? I'm suspicious it didn't really. No? So let's try now from... Let's go back to 1. Because what happens, I mean, to the extent I've hopefully made some sense of feedback and chaotic algorithms, what actually happens is that the previous state makes a difference to the current state. Right, that's your time variance, that's your nonlinearity. So actually, I'm really curious if it's going to happen, but I might as well get a different sound against the 290 if I start from 1 instead of 240. Curious. Oh, let's start. Okay, it will take a while. You see? That's exactly what happened. I have a totally different sound as 290 modulation depth now that I've started from 1 instead of starting from 240. So you see how the whole history actually contributes to what you get in the end. Because this is now a chaotic feedback loop. It's a nonlinear dynamic thing. It's a lot like turbulence and all the other interesting things in the universe. So yeah, I mean, make sure that you don't try to do the same thing twice. It won't work. Cool. All right. So that's the basic thing here. I mean, first of all, a ton of interesting stuff. So I mean, we're gonna go to the gig at 7. I've talked to Bolaj and he was like, yeah, you guys have to come, blah blah. So we won't run the whole class. So we won't take a break in the next 45 minutes. We need some time to walk over. But what I would like you to do is do the basic exercises. So first, well, I'm not even sure if... I mean, I've drawn it already, right? So it would be a bit futile if I give you this as an exercise to draw it, because it's there. But the interesting thing that we can do here is we can induce a delay. Okay, so I'm going to make first an intermediate exercise, okay, whereby I will ask you to produce this patch. Okay, so I'm going to take just some kind of whatever FM26, the best age in the world for females. I hate to be sexist, but I love to highlight differences rather than say everything is the same. And then 26 modulation frequency, modulation depth 50, just because 43 is the best age for men. I've just turned 43 last weekend, so I can testify. Modulation depth is 50, carrier frequency is 500 hertz. This is 26, okay? So this is something that you've done already. And then what I'll ask you to play with or do at this stage is introduce a delay. Delay.ar. With delay, we also have the different kinds of interpolations. So we have delay N, which is no interpolation, delay L, which is linear interpolation, and delay C, which is cubic interpolation. Because you should be able to understand that if I do some heavy delay time modulation, I might at one point want to read a sample which is delayed by a very tiny fraction of a microsecond, which is what we call an intersample delay time. So a decent delay line actually has to interpolate. So if you ask it for a certain given delay time, it will never be bang on the multiple of a sample duration. So it will always be somewhere in between. So in order to be precise, all these delay lines are interpolating. You understand interpolation, right? Creating a value between two fixed numbers. So, and in this case, delay C will sound the smoothest. It will have the least aliasing artifacts going on and so forth. So that's what we're going to do. And, well, just to make this a bit fun, obviously, I will ask you to modulate the delay time with another sine oscillator. And this one should run, well, what should we give it? 6? Best age for a kid. Or for a pussycat, maybe dogs. Okay? Try and fix this. The question here is, what is a good question? Would this work? It's always a good thing to consider what are the values, right? That's the kind of level I'm trying to set you guys up with, that you truly deeply understand this stuff, rather than be like, well, there is this one thing block and I connect it to the other one. It maybe does something, maybe not. So I would love to give you the power to, experiment with full cognition, with full understanding of the domain. So one of the things which is really useful to always ask yourself, okay, what are the actual values in this patch at which point? The other thing to ask is, what is the spectral content, right? Is it a very slow signal? Is it a fast? Is it a broadband and all the rest? So here the question is, what comes out of this sine oscillator? You know it, it's -1 to +1, right? So what I'm saying then is that my delay time, it's useful to specify that. So this is my delay time. So my delay time would actually go +1 -1, which is potentially problematic because, did I tell you this joke? One of the most horrible DSP jokes. What happens if you create a negative delay time? You get a Nobel Prize. Because you've just traveled to the future. So you can't do that. I imagine you can't do that. Please challenge me. Please prove me wrong, like with everything. Okay, so you don't really want, in this context, you don't want to try the negative delay time. So a good thing to do, how would I omit negative delay times? Well, I can just range it, really. Maybe I'll just do the quick thing. I mean, it's always useful to specify these inputs, right? This is a frequency input, and you saw me do this. I'll specify a range, which is 0 to 10. Okay? Just so we don't get negative. Okay, cool, guys. So this is a little task. Please try to code it, and we'll... So we had some solutions, some good solutions, which is great. Now, the interesting thing here to note, so I'm going to build the solution as well, but I'm going to build it slightly with a slight detour, because there is a punchline embedded in this bit. And the punchline is that modulating the delay time modulates the frequency. You see, because that's your Doppler effect. So what happens if I just do the delay time modulation? So I'm going to just start with that to demonstrate it. Let me just start a new one. It's good to see things afresh. So what I have is I have a sine oscillator at, today's number is 92 Hertz, and that's what it is. So if I take this and I delay it max delay time 10 and delay time 3, what's gonna happen? Well, nothing. Why not? Well, actually it did. It started 10 seconds later, right? But you see, because it's a kind of a funny thing to make sure, you know, you fully embrace the fact that delaying something doesn't do anything unless you have the reference, right? So it is the same sound. It won't do a thing. Now, the really cool thing is that if I take the delay time, it was 3 seconds, and instead I take a sine oscillator at 3 Hertz with a range of 0 to 2, that's what I get. You guys get it? So actually the only thing I've done to the sine oscillator is I have delayed it, and the delay time is modulated by another sine oscillator. And actually we already get a bit of that behavior. Which I cannot come to terms with. Maybe tomorrow I will, you know, I'll have a dream or in the shower. But this, as far as my expertise, it's not supposed to happen. Because we have nothing that would produce a change over the first... No, I don't think we do. which is funny. Okay, I'll think about that. But in any case, the punchline here is that's what happens. You see, so essentially, I could probably do something very similar. The only thing that I will struggle with, I could make this an actual FM patch, whereby I take the A, it's just the question of the range. So in this case, well, I just don't know what it could be. 200 to 1200, maybe something like that. So actually this sound, which is your basic FM here. Oh, except, sorry, because that has to be now 3. Right? This. So obviously the range is larger. I mean, I'm not sure if I'm doing well trying to make that. It's not the same. It would take me a while to figure it out if I could. But there's something really weird with this patch. But in any case, the point is that that's what happens. If you modulate the delay time, you actually get another oscillator, essentially modulating the frequency. So what's the big difference in usability of these two frequency modulation techniques? Well, the big difference is that I can do this one to my talking voice or anything else, right? If I take A equals audio in, well, I wonder how this one will work. Channel 0, I guess. And then keep it close to the, and obviously this was a bit large. Oh no, sorry, I should have done that here with the delay. So instead of a sine oscillator, see, because I can do frequency modulation only if I have an oscillator with a frequency input, right? But if I have a delay line and I modulate the delay time, I'm actually getting the same effect. So I can actually do a vibrato on an incoming signal, or if I do some really mad modulation rates, then I can get some FM type sounds as well. So let's see if that works. Hello, 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 hello. I'm not sure about the microphone setup here, to be honest. And it seems like it's not really doing the thing. Let's see. Sound in, is that a better one? Yeah, I need to offset because I'm not sure how the numbers work out with this. Okay. So actually now it's doing that delay time modulation on the input audio. And obviously if I can also do a feedback through audio, right? So if I push this, okay, and that's still quite a large range. Let's try this one. Ooh. You see, now it's my voice. And it's still quite a large range. How about this one? Hello there. I am the most horrible lecturer in the world. I've proven the point, I guess. Okay, so that's this interesting thing that actually delay line modulation is your FM for any arbitrary sound. Make sense? Cool. So then the final exercise will be to do this, and now you see that I can actually simplify it So the only thing I need is delay the sine oscillator like that. What am I saying? What am I saying? Because what I'm trying to do is strip it down a bit. So I do have here an input, which was the sine oscillator. Yeah, probably best off just leaving the two. So I'll ask you to try and complete this exercise, whereby on top of this, we also have the feedback, which looks a bit like this. So the actual sound coming out, but that's the point, because actually I can, let's simplify it. I don't need the FM because I want to show you the fact that you don't need the FM, really. You don't need any of this. As soon as you delay a sine oscillator and you modulate the delay time like that, if you feed it back, it should get very exciting. Okay, so let's see if you guys can make this one happen. The names are just as previously, so we have the feedback amount and the carrier frequency, except that the good thing to do, because you cannot, typically it's not a good idea to put in two parameters, two values to the same parameter. So you see I actually have an adder, explicit adder, because that's what needs to happen. I'm adding the fixed value, which is the carrier frequency, the center frequency for this oscillator. I'm doing the other FM with the delay line. Well, now I know that this is quite radical. Let's just leave it 0 to 1. And then I'm feeding it back. And then this here will be my feedback amount parameter. And this here will be my... No, I don't have a parameter here. It's here already. This is my carrier frequency. Okay. Let's see if you guys get it in 10 minutes. And then after that, I'll probably code it. All right. So I will try to clarify this and show it to you guys at this stage. So first of all, a bit of correction, because this doesn't look too good. It should go the other way around. So it's going up there. And actually, probably a good intermediate step would have been to actually put in here the UGens. So actually, if this is local out, and then there is a local in there, then essentially what happens is that, well, actually it depends where you do the multiplication, but I'm going to do it here just because it's visually more appealing. That actually what you're doing is you're sending this to local out and receiving it in the local in, and the link here is implicit, right? So I can probably do something like dash, something like that. You see, that's essentially what you're looking at, because you're inserting the local in and out. I mean, you could insert it here. Actually, probably in the code, I will be inserting it here. Right? But you can do it here, do it there. You can do it anywhere, really. But that's the point, that somewhere in the loop, there has to be these two UGens doing it. Okay, so let's see the code then. So this was my delay. I'm going to revert back to a sine oscillator. Maybe I shouldn't, who cares? Let's do this with my voice. And then the point is that this is now my, well, I'll call it a Z, like the last letter, the thing that goes out. So what I'm going to do is I'm going to do a local out.ar, and I'm sending out the Z, and I'm going to listen to the Z. And then here, what I can say that actually the sound in is that plus Z. Okay, and then here I could set the two parameters. So what I had is, well, I'll just call it feedback amount, and the carrier frequency is not there. So I will start with feedback being 0.9. Okay, I don't want to blast things. Plus Z. Okay, so sorry, plus exactly local in.ar one channel. Okay, so that local out comes here, becomes added to the sound, and that's that. Hello, hello, hello. Shh. Shh. Okay, so that's with a fairly controlled feedback. Now the fun begins, I hope. Uh-huh. Well, that's dead. As I said, this can happen easily to chaotic stuff that it blows up. Was that too much? It seems like I don't have a really good one, because if it blows up with 1.9... Did I just kill it altogether? I hope not. Looks like it's a mess. One thing you can always do to get good stuff out of this as well is you can invert the feedback thing. So you can actually set local out Z times F, and as soon as you make this a negative value, you're actually inverting the signal in the feedback loop. Wish you luck. But it seems I'm out of luck for today. I've killed it. So, good work. And we will continue tomorrow. Yeah? Try to pack up really quickly.